Welcome, everyone. I'm David Bader, and I direct NJIT's Institute for Data Science. This week's Data Science Seminar Series at the New Jersey Institute of Technology has Leman Akoglu from Carnegie Mellon University speaking on graph-based anomaly detection, problems, algorithms, and applications. Dr. Leman Akoglu is the Heinz College Dean's Associate Professor in the College of Information Systems and Public Policy at Carnegie Mellon University. She holds courtesy appointments in CMU's Computer Science and Machine Learning departments, and she directs the Data Analytics Techniques Algorithms Lab, or Data Lab. Prior to this, she was an assistant professor at Stony Brook University in computer science, since receiving her Ph.D. in computer science at Carnegie Mellon in 2012. Her research interests are in data mining, knowledge discovery, graph mining, machine learning, and online media analysis, with specific focus on identifying and characterizing patterns and anomalies in large-scale, time-varying, multimodal data sources through scalable computational methods. Her research has received numerous publication awards, and there are many of them. I'm just going to list a few. Best Research Paper at Siam Data Mining, both in 2015 and recently in 2019. Best Paper at ADC 2014. Best Paper at PA-KDD in 2010. And Best Knowledge Discovery Paper at ECML PKDD in 2009. She holds 3 US patents filed by IBM TJ Watson Research Lab. Dr. Akoglu is a recipient of the very prestigious National Science Foundation Career Award back in 2015 and the US Army Research Office's Young Investigator Award in 2013. Her research has been supported by NSF, the US ARO, DARPA, Adobe, Facebook, Northrop Grumman, PNC Bank, and PwC. So I'm very pleased to introduce Dr. Leman Akoglu.
Hi, everybody. Thanks for the invitation to Professor Bader. I'm very excited to give this talk. This will be the first time I'm giving this. I've worked on graph-based anomaly detection since my PhD years, almost 10 years ago. So very excited. And thanks to those of you who are in attendance. I regret not seeing you in person, yet I really hope you will enjoy the talk from the comfort and safety of your homes. So let me get started. So let's start with defining what an anomaly is. Well, an anomaly is really observations in collections of data that stand out. So typically those do not obey the norms of the data. And as in this picture, they typically signal some faults or discrepancies in the system. Anomaly detection has many use cases, many applications, from cybersecurity to surveillance, fraud detection, for example, in Medicare and insurances, credit card fraud, detecting counterfeit, advertisement fraud, opinion fraud like fake identities and sock puppets in reviewing systems, and many more. So anomaly detection has many faces, and it finds a lot of applications. But when it comes to formalizing the definition and the detection problem of anomalies, we can talk about 2 settings. In the first case, we would have some concrete problem settings that are well-defined. Those are especially for point cloud data, where we're given these points in some feature space. This could be high dimensional, but for illustrative purposes, I'm visualizing 2-dimensional data, let's say, with 2 normal clusters of points. And in this kind of setting, people typically talk about 3 kinds of concrete anomaly detection problems. The first one being detecting these isolated points in space that are called global outliers. A second scenario is these slightly off, contextually different from their maybe surrounding nearby cluster called local outliers. And we can also talk about these groups of points that are kind of misbehaving or standing out collectively, called collective outliers. So these problems in feature spaces is well-defined, and I will draw in my talk analogies to these three concrete problem settings in the graph domain. Moreover, in the second side of things, the real world is a little bit more complex. So usually the anomaly detection problems in the real world, like the ones I already showed you, do not really come in this format. So we will see a little bit more on that topic, where in the real world, we typically get the problem as, here I have a lot of data, find anomalies, right? So this is not formally well-defined. For example, in accounting, a business woman could come and say, I have millions of transactions that I've recorded in my database, find me abnormalities. And when I talk to domain experts for solving anomaly or fraud detection problems in the real world, a typical conversation goes like this. The business person will say, we heard you work on anomaly detection. And I get very excited. I say, yes, tell me more, please. I'm excited to hear more. So they say, we have lots of data and we want to find anomalies in it. Can you help us? And right, so I wonder what the real problems are. So A, why do you want to detect anomalies? And B, what do you consider to be an anomaly, for example, if they know? And they may tell me the real problems, right? They may say, we want to find errors, inefficiencies, malfeasance in the accounting system, for example, because we want to save money, right? The end goal is actually to make or save money. We also want you to find anomalies that we are not aware of, right? Called is unknown unknowns. So, okay, so the problem is still not concretely well defined, as I showed you earlier, as in this global, local, or collective outliers. So it's still a little bit vague. Moreover, they'll come back and say, oh, by the way, we don't want too many false positives. Our data is in a cloud, so it's in a distributed platform. We have very limited budget. Usually they don't want to spend a lot of money to save money, right? So for example, they say we don't want to spend money for auditing. So we can put this formalism into this format, which is typically how you would solve problems, right? Given data, find anomalies such that there are some constraints that may come from the domain or the system. So in that scenario, I find it helpful to start with the data. So tell me what data have you, do you have? And this way, maybe this will help me to formalize the problem a little bit better, knowing what I can detect with the data that they have. And in that situation, almost unmistakably, in many, many scenarios, especially those related to fraud detection, the underlying data will be relational, so that we can actually build a graph and study the problem from a graph point of view. That's why the talk is focusing on graph-based anomaly detection, and I'll try to convince that this happens in many scenarios. For instance, in fake reviews detection, we will have these users interacting with businesses by writing reviews, positive or negative. In tax fraud detection, we'll have companies that employ certain employees, and the share of resources like these employees will create these relations between companies that will help us detect fraudulent ones. In accounting, obviously transactions between accounts are unmistakably relations that we can use to build graphs from. And in medical domain, like Medicare fraud detection, we talk about physicians relating to patients and who are maybe operating on these patients on certain hospitals. And moreover, we may have some referral links between physicians. So these are all can be again captured in terms of a graph. So it's not a freak occurrence that we will use graphs for anomaly detection. And this has been recognized many, many times. So in 2015, we wrote one of the few surveys on this topic, followed with several tutorials, and I'm giving you some resources if you're interested in this specific subject area. So let's talk about the challenges in solving this kind of underdetermined problem, right? So given data, find anomalies such that some constraints. So first of all, the data, which in this case I'm going to consider is a graph, may have some heterogeneities. So different graphs, not all graphs are the same, right? We may have graphs with node or edge labels. Nodes may have attributes, multiple edges, edge weights, timestamps, and so on. Moreover, we may have some metadata in addition to the graphs, and we may wonder whether or not to fold metadata into a graph representation. With respect to anomalies, we need to define what an anomaly means in the context of the problem. Of course, as I said, some concrete problems exist, but in some other scenarios, real-world settings, defining exactly what an anomaly means, how we detect that will be tricky. And data heterogeneity really exacerbates this definition problem because different graphs may invite different kinds of definitions. Finally, we want to solve these problems under certain application requirements, such as maybe the data is massive, distributed, or streaming. Some applications want attribution, which says who contributed to this fraud, right? Identify the entities in the system, or explainability, meaning why do you claim this to be an anomaly, right? So we want to, these are sort of the challenges associated with formalizing the problem. So now this is the outline of my talk. I'm gonna talk about graph-based anomaly detection in two aspects. In the first part of the talk, I'm gonna talk about these general purpose solutions to the problem that I have worked on, drawing analogies to these global, local, and collective outliers in point cloud data, and basically analogies in the graph domain. And here the problems will be well-defined, relatively well-defined. Then in the second second part of the talk, I'm gonna show you a little bit of more specialized solutions to very specific problems in concrete, specific domains, for example, particularly accounting and computer security. So let's get started with this global anomalies in graphs. So here we are given this big graph, right? It's very messy. Consider a plain graph, plain meaning the nodes do not have any information about them, no labels, no attributes. The graph may have weighted edges, and the edges may further be directed. And what we want to do here is to convert this graph into this feature space that we are comfortable with, right? As I said, there has been a lot of work in anomaly detection for point cloud data. So if we can effectively convert this graph into this kind of format, we know how to detect outliers, right? For example, points that deviate in this feature space would be the global outliers. The question is, how do we do this transformation? Particularly, what is this feature space? So in this very first, one of the first papers that I worked on during my PhD, we built this very simple tool called Oddball, which looks for each node called the ego to its one-hop neighborhood, basically induced subgraph of its neighbors, immediate neighbors, right? Which we call an egonet. And we extract features from this egonet and try to find patterns in this egonet feature space. And then outliers will be points or nodes that deviate from these patterns. Here's a very simple example of what we mean by a pattern. So if you look at the number of neighbors of each node versus the number of edges in the egonet, we observe that these follow some sort of power law distribution or power law-like distribution in log-log scales, where the more neighbors a node has, the more edges in the induced ego network. And this is super linearly so. Here, the slope in logarithmic scale is 1.35, which demonstrates superlinearity. And when we look at the bounds of this thing, a star would lie on this black dotted line with slope 1, where the number of edges is equal to the number of neighbors. This may indicate if the star is very big, for example, like the point over here, a telemarketer, a spammer, a port scanner, those kinds of anomalies in a system. And on the other side, if we see a point on the blue line, that would be a near click structure, maybe some sort of a discussion group or some fraudulent activity trying to boost their ranking. Here's a real example of this same pattern I showed from a post citing each other, hyperlinking each other in a posts forum, where a number of nodes correspond to the number of citations for a post, and the number of edges is the number of cross citations, right? So on one end, we see these very big stars. So for instance, this post was about Hurricane Katrina that was linking to many other posts about donations. So it attracted a lot of attention for collecting money for the hurricane. And on the other hand, we see these Clicklike Anomalies where bunch of accounts created by, or hyperlinks, websites created by the same person linking to each other, maybe to boost its page rank, for example. In another data set, we look at campaign donations, this time studying the number of nodes in the EgoNet versus the total edge weight. And this corresponds to the number of checks received and the total money raised in a campaign donation. And we find anomalies like these, like John Kerry in 2004 raised a lot of money for the number of checks that they received. This person, James Jr., received only a single check, very big single check, which is surprising. And the other side of this anomaly is this person who actually dropped out of the elections and returned all the money, leaving him only $5. So these kinds of things we can observe easily in just 2D. And again, these are global outliers, meaning globally anomalous nodes in a single graph. Next, I want to draw an analogy to local anomalies in a graph. So I'm going to motivate this problem with this illustration. Imagine this simple graph with two communities. And each node in this graph has a number of attributes. So we call this a node attributed graph. And typically when we look at the community, we want to understand what makes these individuals click, right? Why they might be coming together as a community. And on the right-hand side, this community is believed to click because they all work at the same location. On the left-hand side, this community is believed to click because they all live in New York City and they're highly educated, except this one individual in the community with a non-Ph.D. degree. So in that case, we call this individual a community outlier. So locally, they are anomalous to this group. The question now becomes, how do we detect these kinds of local outliers within a community? More formally, we are given this graph with node attributes for each node. A user comes in to tell us what kind of communities they're interested in. So provides us some exemplar nodes of their interest. We infer these bolded attributes that make a community click based on the user's preference, and then go ahead and extract what we call these focused clusters, which are dense in the graph structure and also coherent in these attributes that we infer to be important. And within those focused communities or clusters, we find these what we call focused outliers, nodes that deviate from the cluster members in some of these important attributes. So this is the problem definition. The sketch here is as to what is going to happen is a user comes in, they provide some exemplar nodes from which we create these similar pairs, and then we randomly draw some pairs and call them dissimilar pairs from which we infer this focus or attributes that are important. For example, these people highlighted by the person may be all some female teenagers, for example. So those would be the important attributes. Given this focus attribute or weight, we go ahead and find clusters in the graph that are of that sort, that focus on these specific important attributes. And if any, we find some cluster outliers within the clusters that we extract. So let's talk about how to extract the focus. Again, the user will give us some exemplar nodes, being the green ones. We find some other nodes, randomly sampled nodes. And in this attribute space of nodes, we do some sort of metric learning where we identify a subset of the features called the focus features that separate these two groups. So for example, the third and fourth feature here are helping us to differentiate. And these are the features that are important for this set of entities highlighted by a user. Given the focus features, we identify these communities in the graph by doing some local clustering. So where we start from a core set, a subset of nodes in a graph, carefully identified, and then we grow a cluster around them as long as the clustering objective being this weighted conductance, where the cuts are weighted by the focus attributes, is improved. And we call a node a focused outlier, which structurally would have belonged to the cluster, but otherwise the edges are weak because they do not agree on the important features or focus features. So a node with many but weak ties is considered to be a focused outlier. So here's an example result from this political blocks graph. This is the cluster we extracted. It's a liberal cluster of political blocks, as the hyperlinks here demonstrate, that cite each other heavily, that hyperlink to each other heavily. And their focus features here are highlighted, the top three. Here, it's about sort of about peace and war related things. For example, this liberal blog did not mention this person was, which is related to this war activism or peace activism, despite in the past linking to these other posts. In DBLP co-authorship graph, we identify this community of heavily linked data mining researchers, where one community outlier is highlighted, who is a person who heavily worked with data mining people, yet their focus is information retrieval. So to summarize here, we talked about anomalies in the context of a local community. In that sense, a point is anomalous or a node is anomalous given a specific context. Next, I will talk about collective outliers and drawing analogies to this definition from the graphs domain. So the problem sketches that we are given again a node attributed graph within which we are highlighting a subgraph. So let's say this is maybe an EgoNet or any subset of nodes, a subgraph induced on those nodes. How would we define whether this set of nodes collectively is normal or not? How do we define normality? And here, when we want to do that, we want to consider internal properties among these nodes, as well as external properties, external connectivities. I'm going to show you to draw intuition a little bit to some example subgraphs in a real graph, from real graphs, where, for instance, these nodes in the inner circle are belonging to the subgraph, and they all share the same, what we called earlier, focus attributes. So they all agree or they click on some specific attributes. And yet, externally, they are either very well separated, like in the right-hand side, or whoever is in the boundary is different in terms of their focus. So we would like these to be high quality or high normality subgraphs. On the other hand, here, the bottom subgraphs, for example, we would want them to be low quality because they are not well connected, nor they share some focus attributes, and their external connectivity is very dense, for example, on the right-hand side. They're not well separated. So how do we formalize this a little bit more? Given a subgraph in a node attributed graph, we want to identify the focus. We want to identify weights for each attribute, such that internal nodes are structurally dense and coherent in this focus, and external nodes are structurally sparse. So either there aren't too many external nodes that they're connected to, or those external nodes are not surprising or different in focus. So I'm going to show you what these things mean in a little bit more detail. Internal nodes are structurally dense. So this is what we want. So we want the subgraphs to be well connected and coherent in focus. For example, in this case, these nodes in this subgraph seem to agree on the fourth and the sixth attribute. Let's say they all like chess and biking. And when we look at their external connectivity, basically neighbors outside the subgraph, we either want very few neighbors, structural sparsity, or we want those edges to be not surprising. So what does this not surprising mean? In real graphs, we'll have a lot of hub nodes, meaning, or we will have some hub nodes with many connections. So for example, in Twitter, a lot of people follow Justin Bieber. Those edges, however, are not surprising because this node is high degree, and even in a null model of random connectivity, preserving degrees, we would expect those edges. And they should not take away from the quality of a community because these are not interesting or surprising. On the other hand, some boundary edges may happen on a subgraph because communities overlap, right? So some people like chess, some people like hiking, and some people like both. So looking only on the blue community, we will see some edges on the boundary due to this overlap. However, the nodes outside at the boundary have different focus. So this way we can also exonerate those edges such that they don't take away from the normality of this community. So hopefully this gives you intuition as to what we mean from a good community or cluster in a graph. And we can formalize these under a measure of what we call normality, which has two components, internal and external. Internally, we want pairs of nodes, every pair of nodes in this cluster C to be connected, right? Aij is one in the adjacency matrix if I and j are connected, zero otherwise. And we want these edges to be surprising. So under a null model, preserving degrees, this would be ki, kj being the degrees of node I and j and being the number of nodes, the probability that these nodes would be connected. So if they're high degree, for example, this probability is very high, which makes the edge not surprising. So we want many surprising edges internally that make two nodes in the community similar. So this is S is a similarity function that takes the node attribute vectors xi and xj for the pair, weighted by the focus vector. So this is a weighted similarity. So we want highly similar, right? All agree on some focus attributes and many edges. So this is what makes a good community. On the other hand, externally, we want either not surprising edges, meaning if this is a not surprising edge, a Justin Bieber edge, do not incriminate, right? Do not take away from the quality. Or if they don't share a focus, if they don't share a focus, the boundary node and the internal nodes are different in terms of the focus, then again, this edge will be exonerated. So this same score given a community, we can pull out W, which is the coefficients or weights for the attributes that we want to infer. These are unknown originally. So we can write it as an objective function that says, find me coefficients such that the normality of a given subgraph is maximized as much as possible. And here, if you look at the right-hand side in brackets, this is all data dependent. So we can immediately compute this from the data. So this is known, W is unknown. To make the problem well-defined, we specify some constraints, including some non-negativity constraint for interpretability. So on real data, for example, given, for instance, these 4 authors on the left-hand side in a co-authorship graph, we identify the keywords that they use in their papers, telling us that these people have collaborated or written papers on this topic. And for instance, even the first, Jamie Angulo, Ramirez Angulo, has many other authors, right, which typically would create a lot of cuttages in the graph. We exonerate those by saying that, okay, these papers written by others are not on this topic, so they don't take away from the quality. And these are the subgraphs that I showed you earlier. So these are the scores that we get from normality under L1 or L2 regularization of the objective constraints. And we get positive high values over here. And for the other ones that I showed, we get negative values, actually saying that they are low quality. So this measure reflects what we started as an intuition. Okay. So here, thus far, I talked about collective anomalies where I said a community in a social network context that is densely connected is very good, whereas a sparsely connected community is not so good. But once you change the context, actually two densely connected sets of nodes may be indicative of fraud. So they may be the anomalies. So for instance, if you look at the network of individuals based on various properties, whether they share kinship or they have gone to the same schools and not, if you put edges between people sharing some of those things, we find that 9/11 hijackers are actually the masterminds are heavily connected. So there are many contexts under which two densely connected groups can be collectively anomalous. And we have studied this as well in two different scenarios that I want to highlight. The first one is opinion fraud, where we have users reviewing businesses, restaurants or hotels, positively or negatively, where subset of nodes collectively reviewing heavily some products or businesses, for example, promoting them, is suspicious, where we can show that leveraging those relational properties of dense connectivity and doing guilt by association type algorithms, we can actually detect fake reviews much better than simply using metadata. So prior here is reflective of just using metadata and not looking at the network properties, which shows that it is not as accurate as using this relational information to propagate suspicion. In another context, we studied social securities tax fraud, where companies create shadow companies, where one company declares bankruptcy in order not to pay taxes. And 2 months later, maybe another company will open under a new name and maybe different address, but they will share some resources. For instance, they may share bank accounts or they may share employees. So for instance, once a shadow company opens, employees, some subset of the employees might transfer. So sharing of resources and looking at these dense subgraphs in communities collectively may reveal fraud. And in fact, just to give you a highlight of some results, using these kinds of relational information again, which is this black curve, the gotcha algorithm that we derived, is better than just using features, intrinsic metadata again, which is this red curve. So bottom line is that the graph-based solutions leveraging relational data could be useful in scenarios like fraud detection, where densely connected communities reveal guilt by association. I'm going to do a quick time check. Sorry about that. Okay, so this brings me to the second part of my talk. Now, thus far, we've seen various solutions that I've worked on to graph anomaly detection, drawing analogies to global, local, and collective anomalies. So those were general purpose solutions that were not really motivated by a specific application. Next, I want to move to this specialized scenario where I'm talking to this business expert who wants to detect anomalies in their data, where the problem is a little bit underspecified or vaguely defined, and we'll try to see how we can think about those problems in terms of graph-based solutions. So that's what I want to talk about. And I'm going to focus on two things here. The first one is system security, specifically advanced persistent threat detection. So this was a DARPA project that I contributed to for a couple of years, where APT, advanced persistent threat, is defined as follows. So a threat agent basically does some intelligence gathering by poking, collecting some information about a, let's say, company network. They will then infiltrate, they'll have a point of entry from which they will try to do lateral movement by going to other servers having entered the network, and from which they will extract or steal some data of interest, right? So this is sort of the workflow. And what we want to do here is to do host level detection, meaning can we run this anomaly detection tool at each host within the network intranetwork such that we identify suspicious hosts as early as possible before the threat agent makes a lateral movement to other machines, right? So in order to do that, the data being collected is this log data, right? What is happening in this host or single machine? Processes are running, they are creating certain events like writing, reading from certain parts of memories and disks and files and so on and so forth. So the problem here is as follows. Given this long stream of events, how can we find anomalous system events? So these log files become terabytes of data. It is a stream coming in really fast. And as you can see, this problem is very vaguely defined. This is nowhere near a concrete problem. So when we look at this general problem statement of given data, find anomalies, we may ask what are the constraints in this particular scenario? And they're as follows. So we want to do real-time detection that has low latency, which means this has to be an online monitoring system that responds very fast, alerts things or processes the logs very fast as they arrive in a stream with low computational overhead, because this system will run on the host while other things are already running on the host. So this will be running at the back end, and it shouldn't incur a lot of computational overhead. It should be lightweight. It should not use a lot of memory, again, because it's running simultaneously with other jobs on this host. And in order to achieve real-time performance, we need to use memory, right? We don't want to go to disk, so this should be only in-memory processing kind of detection. In this log file, what is being done is that every logical flow is tagged. So what does that mean? Logical flow could be watching a video or writing an email or building a PowerPoint presentation, right? So those kinds of logical flows happening on a host machine are tagged. So events associated with each logical flow will have different tags. Moreover, as we record the logs, these events may interleave. So I may see events from one logical flow, then I may see event another one, right? And so on and so forth. And one thing we are not seeing yet is that this is not a graph on its face value, right? How are we going to think about this problem in terms of graph-based solution? We can see actually each event is a directed edge. So here, for instance, a fork event creates another process, and a read event, for instance, reads from a particular port, a particular data, and so on and so forth. So we can actually think of each event as a directed edge, and these directed edges would be time-stamped, arriving over a stream. So edges to each graph or each logical flow is arriving over time in a very fast manner, and multiple logical flows may be happening simultaneously in a host, because different events, you may be typing an email at the same time making a presentation. So we can imagine that these graphs are many and simultaneously growing as the log data is being recorded. Another critical thing here is that the universe of labels is unknown. So I don't know how many, so this is a labeled graph where, right, so the port ID or file name or these kinds of things are node labels, and I don't know the universe of labels. This is not a static database, this is evolving, so I may be seeing a new file over time. So the node label universe is unknown. So then the problem definition is, given these graphs simultaneously evolving, how can I detect the anomalous ones, the anomalous logical flows? The way we want to think about this problem is by first representing a graph. Here we used k-shingling, basically looking at subcomponents of a graph by splitting a graph into some subgraphs. For each node, we look at a one-hop neighborhood in this example, traversing in the timestamp order of edges. So for instance, A, X here is an edge label. So A, X, B, Y, C would be one hop, one shingle of node A. Then we could go to B and we could say B, first edge happened at timestamp 300, B, P, E, O, D would be the one shingle of node B. And we do this for all the nodes, creating this set of shingles. Given another graph, we could do the same. And now when we talk about anomaly detection, we use distance-based anomaly detection by comparing the graph representations of these graphs. So if you want to think about the count of each unique one shingle that occurs across all the graphs that you've seen thus far as a vector representation of a graph, the entries depict the number of each shingle graph exhibits. So given these two vectors, now I can do Euclidean distance, cosine distance, I can do anything because now the graphs are in the same space, even though their sizes may differ. The issue, as I highlighted before, is that these graphs are growing, meaning that the entries will get updated, right? So I may observe another shingle of that for graph G, in which case I need to update my counter. So over time, vector entries needs to be updated. And what is more critical is that the vector dimension may increase because, again, the universe of labels is unknown. So when new edges are coming over time, I may create one shingles that I've never seen before. So in that case, the representation dimension of this vector is actually unknown in a streaming scenario that comes from the problem constraints. So we'll approach this problem, so we'll solve this problem by creating graph sketches. First, let me tell you how a sketch would work in a static scenario, which doesn't work for us. I'll tell you why. And then I'll show how we can actually solve that problem in a streaming scenario. So to create a graph sketch, we will create projections. So we will draw L random projection vectors, and these could be sparse as well, but in this scenario, we are only using bit vectors with plus or -1 entries, and projecting the data, meaning this shingle counter representation of a graph by dot producting these things. So dot producting L times gives me a sum, and the sign of that sum will give me a bit. And I'll do this L times to create an L-dimensional sketch representation of a graph G. So I would do that in the static scenario this way. Unfortunately, right, so there are two issues with this. One, when I get a different graph, I will need these projection vectors to be in the memory, and there are L of them, and also S, which is the universe or the size of the shingles, can be very large. So in that case, I don't want to actually hold these things in memory in order to do projections for future graphs. Moreover, what is more important is I don't even know what S is. So I can't even, so because the shingles may change or grow over time, so I am actually unable to, even if I wanted to, even if I had infinite memory, I'm unable to create those a priori in a streaming scenario. So this wouldn't work, but we can actually create sketches in a stream setting still by using, instead of projector vectors, hash functions h1 through hl that take a shingle and map it or hash it to a value either +1 or -1. So in a static scenario, I would take my shingle counter vector z for a graph, and for each shingle, I would multiply the counter with the hash value, sum all of those things. So this is actually doing a dot product, as you can see, on the fly, right? This is a dot product on the fly. And then I could take the sign of y to get my L dimensional sketch in the static scenario. Of course, I don't want to deal with static data. The data is coming over time. But since this dot product is done as a summation on the fly, I can actually handle this in a stream as follows. When I see a shingle S, no matter whether this is an existing shingle that I've seen before or a completely unique one, doesn't matter, I will feed it through the hash functions, which spit out a +1 or -1, which I update my dot product value with. So I may actually add shingles or I may subtract shingles if, for example, I want to ignore some historical part of the data. Or so in that case, as you can see, these are not only being not stored in the memory, right? I don't actually hold such vectors in memory. I only have my hash functions with their high parameters in memory. But also I can actually process new shingles that may emerge over the stream effectively without worrying about whether I've seen them before or not, because the dot product is additive. Okay, so this is all I wanted to say here, given the time, about how to deal with this problem, how to think of it as a graph problem, and then how to incorporate system requirements like stream processing into the problem. Now I want to talk about a different, again, domain-specific problem, where, again, I want to show you how to think about the problem from a graph point of view, and also incorporate system requirements. So in here, we have accounting data, where the data is being recorded following this double entry bookkeeping that is the bread and butter of accounting, I learned. So here, every journal or every transaction you may think about, they call it journal entry, is recorded as a row of entries. So for instance, a company may buy two things, like maybe you are a delivery company and you buy a truck and you hire a driver. So in that case, those two items will be itemized in your journal entry. You spent this much for the truck and you spent this much for the driver, and maybe you pay some tax on the truck, so it also recorded this way. Those are credit entries. And now you have some assets. So the assets accounts are updated by the total amount, because the driver and the truck are now your assets. And everything in the rightmost hand side will sum to 0. This is called double entry. Both credit and debit are recorded in these kinds of journal entries. And those journal entries can be very complicated, meaning they may involve many, many unique accounts, and they may run like several 100,000 lines. Some transactions are very complicated, like, okay. So the problem here is, given millions of these journal entries, right? So every transaction is this kind of report. You have millions of them, let's say in an annual year of a company, you want to find anomalies. So the problem again is very underspecified, very vague. It's not clear how to formally define it. An anomaly here could be something like entry error. Maybe we didn't want to put the money on the assets, we want to put it on the revenue, or misconduct. Maybe I put the money into revenue just to show that the revenue of the company is very high so that the shareholders are happy, right? So some employee misconduct may be there, whoever is doing the bookkeeping. So in this problem framework, then what are the constraints in this problem? There are several constraints, but the main requirement for this problem is explainability, because if we say that some journal entry or set of journal entries is anomalous, they want to know why the detector thinks so before they push it to audit, which is expensive. So again, you have not seen graphs yet. So how is this a graph problem? Well, actually, the journal is a transaction, so it's simple to think about as a graph in this case. Right, so the simplest journal entry has two lines, which says credit, debit, right? So I buy something, I pay something. So it becomes the graph with two nodes, one directed edge from account to account. Note that these nodes, accounts, have types. So it could be a revenue account, sales, revenue account, expense account, cash account, so different types, so which are highlighted in color in this case. And in the previous one I showed, the graph's a little bit more complicated. It has 4 nodes and 3 edges, reflecting those transactions. And in some scenarios, again, the journals may run several 100,000 lines. So the graphs may have many more nodes, up to several hundred. Indeed, I want to just show you, because maybe some of you like to look at pretty graphs. This is a transaction graph of journal entries from a company that I work with over a 10-day window. So one thing you notice is that, again, the nodes are labeled, right? So every label depicts a certain type of account. And the other thing you notice is that there are many, many multi-edges. So there are many edges going from one node to the other node. These are happening because the journal entries are itemized. So even if you bought 2 trucks, we will have the line item 1 for track 1 and line item 2 for track 2, which show as two separate transactions. So we'll put two edges in that scenario. That's why this is a very, very, very multi-edged graph. So given, given many of those graphs, right? Going back to the problem statement, many millions of such graphs, where now each journal entry is depicted with this node labeled multi-edged graph, find anomalous graphs. So that's how we kind of boiled the problem down into a graph-based problem. And in order to approach this, we use anomaly detection via data description or data encoding. I will give you the idea very quickly, and because limited time. But data description basically says, try to explain the data with a model. So G here is the graph database, set of graphs, the set of journal entries. Try to find a model denoted as empty here that is small. The length of the model is small, and the explanation given the model of the database is also small. So it effectively explains the data. So if you think about compression, right? If I have a model that compresses the graphs in the data as efficiently, effectively as possible, while the model being small, then this is good explanation or description of the data. And here the model is what we call motif table. So because these graphs are labeled graphs, we are going to talk about subgraphs with labeled subgraphs, G1, G2, G3, that are motifs of certain stuff, certain structure. And the motif table is a two-column table where on the left-hand side you see these subgraphs, on the right-hand side you see the codes for these subgraphs. Codes, the codes themselves are not important here, but their length matter. So the length is actually inversely proportional to the frequency. So the more I see in the graph database this motif, the shorter their code length will be, such that once I replace all of those many occurrences of that subgraph across the database, I will compress as much as possible. Right? So this is coming from Shannon's entropy. And given a graph in the database like this one, graph GJ for journal J, I will try to cover, having learned this motif table that minimizes this objective, I will try to cover a given graph by really depicting all its edges with a subset of these motifs. So for instance, the first motif here, G1, occurs 3 times in this right-hand side graph, depicted with different dashed edges, right? 1, 2, 3. And the other remaining gray edges need to be covered with other motifs. So, but we will have to cover all the edges. And eventually we will add all the code lengths of the motifs, however many times we use them, that we use to cover a graph. So if we have many graphs or journals in the database, let's say first graph I used 5, motif 1, 2, motif 3, and 1 motif 45 to cover this graph, I will add the code lengths of those motifs. And for instance, graph 2 here is using 4 of the motif 200, which has very high code length, which means that it is not frequent enough. So we will highlight those graphs with high code length to be anomalous. And further, we can go and look at exactly what that G200 was in the motif table and try to interpret why this would be an anomalous situation in order to help us with interpretability, which was one of the requirements of the problem. Okay, so now we show that these perform really well. And one thing I want to quickly highlight is that we compare to graph representation learning methods that do not do well, which I want to finish my talk with. So I'll spend 2 minutes to talk about deep anomaly detection, which is a very growing recent trend. It has not overtaken yet, but soon it will be an explosion of things that I predict on deep anomaly detection, because as you know, representation learning has transformed many applications in NLP, like translation and query, Q&A, recommender system, etc. So we may ask ourselves, why not we use deep learning to automatically learn data representations or graph representations for anomaly detection? And this has been recognized in recent surveys in many last years. And these ideas are discussed in the context of point cloud data, but they easily transfer to graph data. where, right, so a graph embedding takes a graph, learns some low dimensional representation of the nodes or the entire graph. So this is called node embedding, this is called graph embedding, from which we can now solve the problem of graph-based anomaly detection in this feature space using any outlier detector off the shelf. So the good thing about deep anomaly detection is that these models can seamlessly handle these graph heterogeneity issue, any type of graph they seem to digest. However, embeddings we thus far found that do not capture they capture general prevalent patterns that are maybe not making them suitable for anomaly detection. So if we just use this embedding technique to find a graph or node embedding, throw it to an outlier detector as a second stage, we don't seem to do as well. But we may say, okay, let's do end-to-end learning. So let's tie the representation learning at the end layer with some anomaly objective. We can use one-class objectives or reconstruction-based objectives. And here, the devil is in the detail, meaning that we found that hyperparameter tuning is a very big key for success because these models come with many, many moving parts, meaning hyperparameters. And if we don't tune them properly, we don't actually get good results. And we are in an unsupervised scenario. Remember that if we don't have any labels, even small, for validation or model tuning, we will actually be in a very bad place. So we are doing some research right now on this problem applied to graphs, where we show unsupervised deep anomaly detection can do really badly because arbitrarily taking hyperparameters could be very bad. But if we have even slightly little data to labeled data to validate, then they seem to shine. But in the future, I see that unsupervised model selection will be a key topic to make deep anomaly detection more broadly applicable. So thank you for all of you for your attention. You can find all the paper slides, everything at my website. I try to give citations. I believe the slides will be posted online, or I'm happy to share the slides as well. Thank you all.
Leman, thank you so much for a wonderful talk. And if anyone here on Zoom has questions, please ask them in the chat. And I know a couple questions have come in. So the first question comes from Jim Geller, where you're talking about the graph motifs near the end of the talk. And Jim asks, is that the same as subgraph matching?
Subgraph matching. Oh, like isomorphism. How do we? Yes, right. Okay, so I understand the question. So I guess this is related to how do we cover a graph given a motif table. So in this slide, let's say I've learned my motif table. So learning is one part. Given the motif table and given a graph in the database, how do I cover it? So the way we do it is so finding the best cover is actually still I believe would be an NP-hard problem, right? Because it is again combinatorial. I can use many different combinations of these. But in order to simplify this coverage, we use a linear ordering. So we'll start from the top of this list, find first the occurrences of the first motif in the graph, delete those edges that are covered, then move to the second motif, right? Find the occurrences of that. If it covers any edges, remove those, and so on and so forth in a linear fashion. And the reason we do, and this is of course, right, not exact in any way or form, but the reason we do it is because these motifs in this table are ordered by quality, meaning that the most frequent motif typically lies towards the top of the list. So that's why we want to first start with covering the most frequent subgraphs in a graph so as to remove as many edges as early as possible.
Thank you. There's a question from Oliver Alvarado Rodriguez, who asks, is deep anomaly detection basically viewing the node or graph embedding in a new feature space and then applying an outlier detection algorithm to this new feature space?
Yes, exactly. So exactly as you said, so you get a graph, let's say you're doing in a single graph. So one thing I didn't maybe point out is that I actually talked about two different things, right? So in the first part of the talk, I was trying to find anomalous nodes or sets of nodes in a single graph. Whereas in the second part, I was talking about finding anomalous graph in a graph database. In either case, right, I'm interested in either node representations or a graph representation. If I'm talking graph database, I want to embed each graph so that it's a point in a feature space. And now I can throw whatever outlier detector, point outlier detector I have off the shelf to the problem. Because I know how to do outlier detection. A lot of people are comfortable with point cloud data, but with graphs, things are a bit trickier. And as you saw in most of the talk, for each different type of problem or graph, right, node labeled, weighted, we have a different solution, which may not be ideal because graph embeddings are so universal. You throw it, they can handle, as I said, any kind of graph seamlessly. So it is promising in the sense that I think deep anomaly detection will help with providing a unified framework to solve the problems. But there are this key issue of hyperparameter tuning. But short answer is yes, exactly. So we will convert everything into point cloud.
Thank you. There's a question from Andrei Kunayev who asks, is clustering-based detection numerically impractical?
Clustering-based objective, numerically impractical.
Clustering-based detection, numerically impractical.
I will need an elaboration on it. I'm not sure.
Okay, so maybe I could ask you a question. I see a lot in the news in stories about disinformation campaigns in social media. Would your anomaly detection on graphs be able to look at the disinformation campaigns and be able to automatically find or identify them?
That's a great question. This is not a domain I've studied, but I believe that the characteristics of misinformation aligns with the problems that I talked about. For example, in misinformation in platforms where there is a reputation system, so we don't believe all the news that we see, right? We look at who is sharing the news. So in reputation-based systems, they try to boost their reputation by either following each other or sort of collecting follows. So creating either clicks by following each other or trying to attract sort of a lot of follows from people that don't know necessarily each other. So this immediate neighborhood can tell a lot about whether a person sharing news is actually trustworthy or not, in the sense that they may stand out in that way. So the way it aligns is they will either be forming dense subgraphs or too sparse subgraphs in order to play with the reputation system. So I believe yes. And in fact, one of the colleagues that I worked in the past, Srijan Kumar, has written this survey paper where he particularly works on this misinformation problem. And in this survey, he actually talks a lot about graph-based solutions. That's why I included them. I included the survey here in the resources.
So thank you again, Leman, for giving this nice talk on anomaly detection with graphs. And I enjoyed the talk today. I hope the rest of our audience did. And everyone should tune in next week again for our data science seminar series. So thank you again, Leman.
Thank you, David. Thank you, everyone. Have a good night.